Hello and welcome back to the DOTS lectures. Last time what we were seeing is this pipeline for taking essentially a system in your system theory and producing a compositionality theorem in the form of a functor out of it. So I'm going to do that again, but here we're going to do it a little more sort of in a way generally, right? So one thing is we're going to take the starting point is we have some category clock of clocks, and we're going to put it into the algebras or maybe I'll do symmetric, monoidal, loose, right, modules, and collax morphisms from the point to some systems theory S, right? And so what is this? This is the data we are starting with. So what is that? That means that for every clock C, uh, we have or I'm just going to call it I. I'm going to treat it as an index. We have CI, which is a map, a collax morphism of symmetric modal loose right modules like this. Which, as we saw above, if in pseudo in nice enough situations, which is fairly common, this is just a system.
The point being that the other data you need to define in theory is like uniquely determined by the structure. Is that
The other data you need to determine a collax morphism here. So it is very important that it be collax. And as we saw last time, I'll just encourage you, dear viewer, to go back and see all the data last time. I mean, I'll and swoop up here, but we saw there was a bunch of extra data, perhaps, right? Corresponding not just to the system and its interface, but also these perhaps this interaction that it had, and very often, and this comonoid structure that it has. And if your system theory was Cartesian, then there's a unique comonoid structure. And if you have a certain nice property that I don't have quite the abstract way to say, but if you have a certain nice property on your double category, which is not terribly rare, in fact, you don't get anything interesting going on here. It's sort of like a little more than a thinness condition. You don't get anything going on the right-hand side of the screen. You don't get any of these the WCs can be identities, and all this stuff can be identities and stuff like that. So that's the situation we're most often in. But in general, like it pays to work at this level of generality, because after we do that, we can note that we can take the comma here, the slice construction. So what does that do, right? This is going to give me a discrete op for vibration in a strict discrete op vibration in SML mod R in SML mod R lax over S. And this is just because it turns out to send it to a strict one. Right? So what does this mean? Well, I have something like this, C, right? And then I take the comma like this, and this is what we call the slice C down arrow S. And this thing here is what we send over here. This is a disc and it is in fact a strict morphism. And then we have our next thing here, which is that we use the fact that this is the same thing as SML mod are lax from S to omega, which we talked about last time, where omega is the systems theory, is the Jan Willems behavioral control theory. Control theory, or atemporal, I should say, as in just, i.e., it is uh, sharing variables, impure sets. So it is specifically its span set, one comma dash acted on by span set. Right, and this is an equivalence, and this was my theorem with Matteo Cappucci, which we covered. And so in total, what you see is we end up with through this process here, we end up with clock to SM L mod lax R S omega, right? And this here is we could call SC comma dash the hum functors out of C, out of the clocks. And as we saw innumerable times over these course of these lectures, the hum functors out of certain clock-like systems correspond to behaviors of systems in a wide variety of cases. Okay. So what we'll see here is that this will correspond to um, uh, I'll just write it like this, SC comma dash in SML mod lax R S comma omega to the C up. There's an op gets picked up somewhere in here.
On the
Yeah.
top, it into lax rather than coax now.
Yeah, so this map is this composite.
Oh, okay.
Yeah. And then this here, this correspondence here is what it means to have powers by category. Oh, that's not C, sorry. It's not C. It's clock. Clock up. So us having powers. Really, there's an op here somewhere that I missed. It's probably in here. Right. Okay. Uh, yeah. Right. The functorialities actually involves the discrete lifting property, and so that goes in the opposite direction because we're mapping out. Okay. Is that all right? Okay. So we'll see what this is here. There should be more. Maybe I should go into the functoriality of these things more carefully, but um, so now we can show basically that this thing is the same thing as span set to the C op or clock op, excuse me, one comma dash acted upon by span set to the clock op. In other words, instead of taking a bunch of lax functors from S into omega indexed by a category clock, we can take a single one landing in pre-sheaves. And this is just currying. So by currying. In other words, we define S C dash at I to be S C of I dash. Right? Or like, yeah, that makes sense.
So we have a lot of clocks. Now, why is it important to have lots of clocks? So this is my point is that we then get a thing landing not in just sets, but we can actually get something landing in precies on some category blocks. So e.g., suppose that S was uh, uh, the more machines with halt. And the following morphisms. So in other words, we have a more machine is S and then S plus halt. I think we've covered this before. We talked about these before in some other lecture, right? And a morphism was one of these. But with an inequality here.
I think it goes that way, although I'm going to double check this.
So where we have the ordering, or excuse me, where we have an ordering where bot is less than every element of S. And so this is um, uh, I'll just say XY. And this is UE, and this is U prime, E prime. So this says that um, X after E equals E prime after phi. And then instead it says that the top, and let me make sure I get this right, is that so i.e. the top one will say, just writing it out here, is that for any I and any S prime,
Is that the right thing?
for any I and any S. Yep. U, so phi of U of SI is less than or equal to um, there we go, is less than or equal to U prime of phi of S y of I, y of E of S, I.
Right. And so why is this, what does this mean? Um, uh, so for example, now uh, it's really not phi, but it's phi like extended by bot, mapping bot to bot. That's okay. So if phi of if U halts, if S and I transitions to bot, right? So if U S I equals bot, then phi of bot equals bot is less than or equal to anything. So we don't actually make any constraints on the things that are about to halt. And that's an important point here. So now we can define, so so consider the category of discrete time linear clocks, which, as we saw in some earlier lectures, was delta inert, whose objects are natural numbers, d and n, which we think of as discrete durations, and a morphism d to d prime is an I such that d plus I is less than or equal to d prime. And the way we think of this, remember, is that d is some duration. Of course, it's a finite, it's a duration having exactly d segments, right? Or, well, let's just say ticks.
Yeah, D ticks, right? Yeah. No, D segments, D segments. So there's 1, 2, 3, 4, D equals 4, right? And then if we have more of them, so 1, 2, 3, 4, 5, 6, 7, D prime equals 7, then a particular mapping, right, is some I that some offset, like for example, maybe 2, sorry, yeah. Am I doing this right? Oh,
If it's that is 2, then I would say like the ticks is number from 0 to 4.
yeah.
Then tick.
I think I want to do 0, 1, 2, 3, 4. That's a little better. Yeah. The numbers are the same, but I'm going to number the ticks. 6, 7. Okay. And now the offset can be up to 2, right? I'll call I equals 2. And then this has to go up to this plus 2, which is actually there. And so that selects a subsequence here. Right? So I'm going to define C. I'm going to define C from delta inert to more bot. Let's call S, i.e. more bot. These are more machines, but they have this halt, and the halt is less than or equal to any element, and we have this kind of morphism, which will be useful. We've covered this before in some lecture, but I'm going to do it again right here. So C of D is going to be equal to, we're going to take the actual D ticks here. So D equals the ticks. So 0 dot 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 D. And this is, of course, D plus bot. We have no choice. And then we have to give it its interface, right? And the interface is going to be D again. And it takes no input, right? And then we have the expose is the identity, and the update here is going to be plus one, except uh, D plus 1 equals bot. In other words, like it runs for D ticks, starting from 0, right? After D ticks, this thing's halt, right? And then a morphism, we have to give a morphism here. So D to D prime. So if I have D to D prime, I need to give a bunch of maps like this. Um, right? And then with this an equation here. And then so what is this map? Well, there's an obvious map I have in this case, right? In the bottom, right? I will call it plus I, right? It's a map that's plus I. If this map is C of I, right? I being this displacement, it's plus I, and then here is just is trivial, right? And then over here it's also plus I. You know. And then the only thing to check, well, that's is that if I shift over and add 1, that's the same thing as adding 1 and shifting over, and that's pretty obvious. And remember that there's only one place where these things disagree, which is that the ladder clock probably doesn't stop at D. It keeps going. But by virtue of our definition of morphism here, we don't ask that it halts at D. We ask that when it halts, we make no constraints whatsoever. And so this is perfectly good. And so that gives us a functor into this systems theory of more machines with halt. Okay. As a corollary of the above thing we just talked about, we get a representable double functor out of C into now its span of set to the delta inert. 1 comma dash, right? And this is, as it turns out, this is in fact a pseudo-functor, which has to do with special features, or I should be careful about that. This inequality is not something that, let me not say that, I haven't checked. It may very well be a pseudo-functor, but it may not, because of this inequality is not in one of my sort of general theorems. You don't know. Anyway, we get this compositionality theorem. And what does it do? Well, it sends a system here to this pre-sheaf. That's why I write inert on the bottom. Anyway, whatever. It's too late. Sends it to this pre-sheaf, and what is it? What is the pre-sheaf? Well, first of all, it's a system there has interface IO. A system here has interface something, right? What it is it's the functor. These are both functors now. Excuse me. D maps to something, some set. And here it is sequences of length D, pairs of an I, the set of pairs of an I, which is a sequence of length N or D, excuse me, to I, and an O, which is D to O. And that's it. So that's a set. This is a functor. It takes in this and it goes to set. What does it do on the displacements? Well, it just selects the appropriate subsequence of these sequences. So these are sequences of length I of inputs, sequences of length I of outputs. And that's some pre-sheaf here. And over here, we get the sheaf, right? Which sends us to, in addition to I and O, also S, which is a sequence of length D into S. But now we have some equations. And the equations are that ES is equal to, well, it's really E after S, but E after S is equal to to O, excuse me, to O. And here, right, it's the other equation that governs this, which I'll maybe write it out for all. So for all T, I'll write it out with T in D for all ticks of the clock. We have that E of S of T equals O of T. And we have that S of T plus 1 is equal to U of S of T, I of T, unless T equals D.
Right? And that's a perfectly good notion of a trace that lasts for D ticks. Right? If T equals D, that equation isn't even really well formed, right? So, and then you also have the projection map here that projects out the I's. Right? And then, of course, you get all the other things we started talking about last time. You get in addition to this, every wiring diagram or morphism on the left, lens on the left, gives you a span, and you get this comparison from the pullbacks, and so on and so on and so on. Cool. So this is an example of a compositionality theorem. See, theorem. In this case, it's lax, although we could go through and check if it's pseudo. I have a suspicion that this will be pseudo. It would be pseudo if we had equalities in the squares. It would be pseudo. And you see the inequalities only come up very rarely. So, but it's worth checking.
Do we know it's pseudo if we take our clock as just the infinite time
Yeah,
one and without equalities? Like,
without inequalities, with the
Yeah.
equalities. Yes, that's true.
okay. Seems like you should get the infinite time behavior from this free sheet.
Yeah. I believe it's pseudo. I only realize right now that I hadn't checked for this. Um, so it should be pseudo. If it is, it would be like a real compositionality theorem. And all we had to do is, and all we had to do was one, define the symmetric monodal loose right module of more machines, which by the way, we can do in a sort of systematic way, as we described earlier in this series. And two, pick some clocks. And yeah. And so that's how you do compositionality theorems in dots. So why do you do this? Well, as we talked about at a previous time, right? This setting here, so note like LTL, linear temporal logic, linear time temporal logic, interprets into presheaves on delta inert. We had a lecture about that previously. So if phi is a formula, um, concerning, say, concerning the states, so maybe I'll transition from this into assume guarantee reasoning, but I don't think I want to start doing that. But let's just say concerning the paths, the traces. Okay, this is called a path formula. You could also take a state formula and do this, right? I.e., we can interpret phi as being a subsheaf of more bot C S of traces of S. Right? We can interpret it like that. And now we can ask, is phi true of S? And that would be, is there a section here like that? In this case, that would just mean that that is the whole thing, every behavior, right? Where this, as you see here, this is the set of traces. And I think in the next lecture, I'll do how you can use this to describe assumed guarantee reasoning. Well, I guess I've only been talking for like 15 minutes now. So. Half an hour? Okay. I think I'm going to call it here. But there's a few more things I want to cover. Like one, I want to cover the compositionality theorem you get. So maybe I'll do continue. Let me do one more of these just to show you the variety, and then I'll go on. But part of the reason is you note that the linear, so the fact that you had this category of clocks, right, connects very strongly with the fact that you have this kind of time, right? This is the category of discrete time linear clocks, and you end up with this kind of logic as a modal logic, and it interprets into this topos, which has a very, a bunch of nice logic in it in which you can express predicates here. And so you can start to do the compositionality of predicates as well, which I will talk about eventually, which goes under the name of assumed guarantee reasoning. But let's see another one of these. Consider ODEs, which remember were a kind of Moore machine. Where we took a manifold S and we took a bundle of
of parameters bundled over observations. And we have our observation. We take the parameters that are valid with respect to that observation, and we give a vector field using those parameters. This was i.e. a parameterized ODE. And as we saw, this is in fact a lens. So this is in fact a Moore machine in the tangency of submersions over manifolds with the tangent bundle. And remember, we saw that you could produce the notion of Moore machine from any such tangency. Right? Okay, what's a clock in here? So here we're going to define clock to be instead of, it's going to be very similar to the last one, but instead of, it's going to be what's called the interval domain. And it's used in Blackboard, Blackboard Bold, but I'm going to call it just IR like this. So its objects are, we have a, yeah, I'm going to make it the one that looks more like a nerd. So its objects are pairs of real numbers. I'll make it like A, B, such that A is less than or equal to B. And a morphism let me not do it. Sorry, I'm doing this one wrong. I'm doing this wrong. I'm going to do the one that makes it look most like a nerd. Sorry. There's the one behavior types and behavior types in time. This is just behavior types. So it's going to be a duration in R greater than 0. And a morphism I is a I in R greater than 0, such that D plus I is less than or equal to D prime. What do you know? It's very similar. I'll secretly say that the delta inert is the twisted arrow category of the natural numbers and their ordering. And IR here is the twisted arrow category of the real numbers and their ordering. Okay. So again, we're going to say C of D is going to be an ODE. So I will make the ODE here. It's going to be a duration 0D. We have T0D, right? And then its output is also going to be 0D. Oh, this is E. And then its input is going to be trivial, which means it's 0D. Which means when I pull back, I get 0D over here. And then now you see that what I'm giving is just a section of this tangent bundle. I'm going to give the constant vector 1, i.e. this represents the ODE. So this, by the way, this represents the ODE. ds dt is equal to USI. And this one represents the ODE. dt equals 1 for t in 0, comma d. And I believe we did cover how these represent solutions to ODEs. So, and again, how do I go to C prime? It's just, adding I. And yes, that is linear. So it preserves this differential equation, right? Okay. No, not just linear. Sorry, it preserves this differential equation. If you move at rate 1 and you just translate, you still are moving at rate 1. So this again, we get this theorem. We get more. Let me call it ODE. We have ODEs. ODEs mapping out of C into span sep to the IR op. 1, comma dash. Again, interpreting as spans. And this one is proper pseudo. Look at me getting all British. It's actually pseudo. And so there's your compositionality theorem. And this is one that you can see in dynamical systems and sheaves. By Vasilakopoulos. I'm sorry. No, like that. Sorry. Spivak and Schultz. Uh, Really great paper. Um, and so, right. So you can see it's representable. And again, we've just popped out a compositionality theorem just by picking the right clocks. Like once we've constructed our systems theory, the point is that the compositionality theorems are implicit in the systems theory as long as the things you're trying to prove them about are representable. And they quite often are. And if they aren't, maybe try to build the right one where they are, right? Another way to understand this is that the task of building the double operatic thing, in addition to the operatic one, is to prove all the lemmas you need to prove about morphisms that represent what you want so that you get a compositionality theorem for free like this. Okay, so you don't just land in this. It's one thing to note that it is, in fact, you can do a little better than this. You actually can note that 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 you actually will land in sheaves on this for a certain topology, Grothendieck topology on this. And you can check that point-wise, right? Sheaves are a full subcategory, so you just have to check that actually the sets of solutions are sheaves. And they are for sort of a very sort of certain nice topologies on this because ultimately you're just considering certain kinds of smooth functions mapping out. Okay, so there's another example. This would be a great time if I trusted myself on a Friday afternoon to write up the Moore machine example. I'm going to try it. I'm not going to go too detailed. So sorry. So let's consider POMDPs. And these are Moore machines for measurable spaces. For the simple vibration on measurable spaces. Although, in fact, it can often be useful to use a more complicated one. Where this is the Giry monad of distributions. Monad. Take your pick. Take your pick of the precise definition of all this, by the way. You could very much use your own favorite definition of measurable and probability monad. There's a lot of analytic details when you actually try to do real categorical probability theory. But what I'm about to say is not terribly sensitive to much of them. The answers you get are going to be sensitive. So now, right, we can say now, let me consider our clock category is going to be to a category of omega, and so and we'll say let's just do omega for now. Standard Borel spaces. Omega, aka sample spaces, with a probability measure with mu. And I need maybe something nice about this. So let me just assume that this measure is isomorphic to the Lebesgue measure on R. If you know about this, you know that there's essentially only one standard Borel space of uncountable cardinality, which is R, and essentially every measure is this one. That's not totally true, but like I have a big blind spot in my knowledge about analysis, so please forgive me for all the mistakes I'm about to make. But roughly speaking, we can take a pretty generic, this is not a direct delta distribution. This is a pretty generic one. You might as well take them to be, they can be infinite or finite. It doesn't really matter. In fact, we can take the whole category with all these probability spaces. It's fine. Like this, and measure preserving maps. Okay. And now I'm going to give you the functor C from clocks to POM-DPs. And this, by the way, it's due to Owen Lynch in collab with Sam Stetton, Eigel, Richel, and myself. Yep. In rapidly decreasing order of contribution. Sorry, I mean, like, it drops off here. um, uh, I was around for this. Maybe appropriate to say. Um, and how you define it is that C omega is going to be the following machine. So its state space is going to be the natural numbers and infinite sequences of elements of omega. And so you want to think of this as the time t and the stream of events. Right? And then here, right, it's going to be, as we know, distribution on n times omega star. And then we're going to do the same thing we often do with our clocks in this doctrine, which is just put this here and that. We're going to take the bottom to be the identity, and the top is going to be the top, u, is going to go, roughly speaking, from n cross, there's a factor of this singleton up here that we're going to ignore, it's this to delta n cross omega star. And what we're going to do is we're going to take t omega and we're going to map it to what I would call something like Dirac delta t plus 1 times sampling from sample from omega prime such that omega prime restricted to less than or equal to t is equal to omega with respect to mu. Okay. So I don't know how public this paper is right now, but there's a paper which explains this in correct detail. But what it is the idea is that omega, right, is something like omega 1 or, whatever, omega 1, omega 2, omega 3. It's a long wait for omega 2, omega 3, all the way on. And then we have, say, t is 3, right? After here, we resample omega prime 4, omega prime 5, and then these are the same thing as omega 1, omega 2, omega prime, omega 3 prime, right? And so a thing to note is that the infinite sequences here, they have there is for Fn, you can define to be the pullback pi n star of sigma omega, of the sigma algebra on omega n, where pi n goes from omega star to omega n is the first projection onto the first onto first n. And that's a filtration of this this probability space omega star. By the way, like as a standard Borel space, that's just still omega, if omega was uncountable, right? And so roughly speaking, the same thing, but we put this canonical filtration on it like this, right? And what we're doing is we're ticking forward along in the time, and we're also going a little bit further down this filtration. We're learning more about our system. And what we're learning about our system is what we've seen so far about it, the events we've seen so far. So it is true that in fact, so what is then a behavior of such a thing, right? It may be good to use instead of using delta up here, it's actually quite nice to use instead of using the distribution moment, it's often quite nice to take it valued in random variables in S, which can be expressed in various convenient categories of higher order probability theory. So see this. Eigel has been also extending this work to work with continuous time. So this also works with continuous time systems, well, which is really cool. Okay, so all right, suppose we have a generic one of these, and we have n times omega star, r. We have n times omega star, n times delta, delta, times omega star. Right, so we have a bunch of maps like this. So first of all, let's write what these are, right? Remember, we have O, n times omega star to O, I, n times omega star to I, and S, which is n times omega star to S, right? And then the thing to note is that, this is a sequence of random variables. These are all sequences of random variables, right? With sample space omega star. Oh, they're all measurable, by the way. We're in the category of measurable spaces, right? So everything's measurable. So now what do we know? Well, we have to put a fun extra little twiddle here, just as we did in the previous ones. You find you have to do this a lot if you want it to work with the non-deterministic system. And that twiddle is that what we want is these squares to commute up to almost sure equality. So, sorry, you want them, that's not correct. You want them to commute in law. So we have we have n times omega star, and here we have, well, this is n times omega star, and here we have O, and here we have S, and here we have O, and here we have S, and here we have O, and that one's E. And what you want is that this commutes in law, i.e. the push forward. So it's worth noting that like the i.e. the push forward, E after S lower star of mu, right? Of it's not mu, it's the mu star, right? Is equal to O lower star of mu up star in delta O. Right? The push forwards of these two maps are equal in law. And you want to add that on to all of instead of taking equations, you take all of these, right? But this is fine. This is fine. And what you end up with is you get these sets of random variables evolving according to law. And where do you end up? Well, you end up again. So as we see, POM-DP, we have another compositionality theorem here. DP. This is not the interesting one. The interesting one is, of course, that S t plus 1 is equal in law to U of ST comma IT for all t. Right? So that's what it means to have a sequence of random variables evolving according to the law of this partially observable Markov decision process. And in fact, it's subordinate to the canonical filtration, the one we put on omega star. Comma dash, this length and span of set to the standard Borel prob op. 1 comma dash. Right? And again, if we quotient out by almost everywhere equality, then we land in sheaves on standard Borel prob. And this is a topos known as, this is Alex Simpson's topos. Topos of random sets. So you can see that very nicely, just like in the pure ODE, in the pure Moore machine case, we landed in sets and we got the streams of the infinite streams of things landing in sets. You see that if we want to do POMDPs, we get streams of random sets. We get random sets of our infinite C streams evolving according to the law of our Markov processes, and it's just as compositional. It's the other things. Okay. So should I do any of the other kinds of doctrines? I think it gets a little more complex with reachability because of the notion. I may want to. This is all symmetric monodal loose right modules, but if you want to get, say, reachability problems for Petri nets, you really need to be using algebras for double operads. But the abstract story is 100% the same, and you just pump out more compositionality theorems like this. So.
Sorry, did you say whether this map is lax or pseudo?
I'm a little worried about this like the fact that we're not asking for them to be equal, we're asking them to be equal in law. So I think if you asked for them to be equal, it would be pseudo.
And there's some general result that you and Matteo have.
Well, it's actually already in my manuscript. It's just in the Moore machine, the one with the strict equality Moore machine ones. They're all pseudo. And Matteo does have an extension of it that gives you an abstract characterization of when that is. But yeah.
Right. Do you have so you've got this nice theory of building these categories of like strict Moore machines, or Moore machines with these strict two cells, or double categories with these strict two cells as like adequate triples, and where you've got some tangency for a pseudo for the cat. Is there some nice way to extend it to these double categories where you've got these two cells filling them? I guess then you're.
Yeah, I'm not sure. I think it would be worth figuring out because they are fairly common. My feeling is that like you could probably do it by saying you have a double category to start with of your squares, of commuting squares, right? Perhaps like a thin double category. Like, see that square on the right? Like, I'll draw it. See this square like here? Think of this as a square in a double category.
Yeah.
And then we try to like build one of these out of like, a thing like that, right? Like a double category with type products, right? And then you, I'm not sure how to do it,
So
but like, yeah,
replacing-
you just like, you say like, I don't know what a square is. You tell me what a commuting square is, and we'll use that.
Right. Okay.
But like, I think that you shouldn't have to know more than that, except that it relates well with products and it composes in all the ways you need a double category square to compose.
Right.
For simple lenses, at least.
Right. Okay. Because these start with a category, a Cartesian gross, or
Just a Cartesian category,
with
yeah, with a section of its simple fibration, yeah.
Right. Okay. So here, but when you were doing,
Which is to say, like an endofunctor, yeah.
right, but like when you're talking about this bottom element, I guess you're mentioning you're working in like a two, starting with like, so like set is one example, but
Yeah.
But if you want that sort of bottom element, you're sort of working in pos.
Yeah,
as the
yeah,
idea.
yeah,
It goes
that's
to the
right.
two-dimensional bit.
There's, yeah, you can, I did write down at one point the correct two-dimensional version, but this case here, I don't think is a two-dimensional version.
Right.
Yeah. And what's interesting in here is like, you might also, another interesting thing to go from this is it would be really interesting to have a notion of approximate homomorphism where you're like, nah, it doesn't commune, but it almost communes, right? Like the next, I'm within epsilon of being a correct homomorphism or whatever. Or like, I'm a homomorphism to the first order.
Okay.
Or there's all these other things. So I think that would be a really interesting avenue, but I haven't really looked into it too well. Yeah, exactly. Yeah, graded enriched Yeah. Yeah. And yeah.
Okay. Maybe we
Cool. I think that's a good place to
Yeah.
start.